Hello, my name is Abdullah and this is my submission for the ENCMP coding contest. My submission is based upon a phenomenon in physics known as simple harmonic motion. The goal is to simulate this at different levels of complexity and then to animate it all using Python. So this is my code and it's quite long as you can see, but despite its length, it's actually quite simple in principle. We have a couple of user-defined functions, for example calculate displacement, which takes time as an argument and returns displacement. These functions are called in the animate function, which calculates the values of these displacements, accelerations, and velocities at a given time and generates a figure. Each figure corresponds to a frame and time. Then the func animation turns that figure and that time into an animation, which is then saved using ani.save as animation.gif. You can see that it's really simple. Like it's not complicated in terms of theory. Actually, a little thing I'd like to point out. Quite proud of this is I've written the code in such a way that no matter what frame rate you choose and what time range you choose, you always get an animation that's in real time. So you could play the animation side by side with the real thing, and you could probably compare it and probably see that it's actually quite accurate. I just think that's quite nice. There's a couple other functions that I've included to make it more fleshed out in the whole code, just to make a better user experience. I'll show you those by running the code. You can see when we run the code, we're prompted with a menu um, with 5 options: change initial variable, make animation, plot resonance response curve, display additional data, and exit. Those are pretty, the titles are pretty intuitive. I think you can probably understand what each of them does. So say we wanted to make an animation. The main purpose of this program, we click Tool, generates the animation. As you can see, it takes a couple of seconds because there's a lot of frames that we need to generate in order to make an animation. But you can see that an animation was generated. See that follows this nice underdamped curve. And that's what we'd expect as physics students. We have the damping ratio as 0.1, significantly lower than the critical damping number. We'd expect something that looks like this. You can see that there's both the real figure, the figure that kind of shows what you'd see, and a plot that shows the displacement against the time. I think that's pretty cool. We can also just plot the resonance response curve that doesn't take any time at all. And you'd see, because it's an underdamped oscillator, we're expecting a sharp peak at roughly 2, and that's the natural driving frequency, which is about what we'd expect. You can display additional data. Wait, no, that's 4. Here we go. So you can see that it's an underdamped resonating oscillator. It will take 93 seconds to reach equilibrium, and the maximum resonance is at 1.99 radians. This is actually expected. We don't actually expect 2. It should be slightly less than 2. Yeah, another thing you could do is you could change the initial variables. So let's say we wanted to set it to critical damping, right? So that'd be 0, 5, 1 mass, 4. I'm keeping everything else constant, the same. I'm just going to change the damping ratio. So we're expecting critical damping to occur at 4 using our formulas. So let's run that. Okay. Now the variables have changed. So now if I generate a new animation, again, it'll take a couple of seconds, but any second now. There we go. And you can see it generated a new animation with a different graph, a graph that we'd expect to see in critical damping. You can see that we're not expecting any resonance of a critical damped case, and you can see that the plot is different for it, and you can compare the two. You can see this is non-resonating, this is resonating. We can display additional data. This time it's a critically damped oscillator as we predicted. It took 4 seconds to reach equilibrium, and there's no resonance. And again, you could repeat this with an undamped oscillator case. You could overdamp it. You could try all sorts of different values, or you could exit the program when you're ready. But yeah, that's the idea. It allows you to play around with the theory and the fundamentals. You can see right in front of your eyes what you'd see as you vary different variables, and you get a very intuitive understanding of how all of this works. Yeah, that's my code. I imagine that one could extend this concept to cover all the topics included in Physics 130, such as waves, optics, and light, perhaps even make a graphical user interface to make it more accessible. I think that'd be a great learning tool for students. Well, that's all from me. See you next time.